Howdy, in this video, we'll discuss stacking fault imaging in TEM. Stacking faults are widely observed in metals with low stacking fault energy and some ceramics. In the examples shown here, you can see bright, dark, bright, dark, bright, dark fringes. These fringes are caused by the stacking faults in the material. Just one slide on what is stacking fault using FCC crystal as an example. If you view the crystal along the 110 direction, looking at the 111 planes, it will have ABC stacking. If you have a stacking fault present in the crystal, the ABC stacking will be disturbed. In the example shown on the right, it has ABC, then ABA stacking. Stacking faults are translational boundaries. In the example on the right, the stacking fault translated the C plane into the A position. The translation magnitude and the direction are described by the fault vector R. In FCC crystals, R is equal to 1/3 111 or 1/6 112. Let's look at why stacking faults can give rise to contrast. If you have watched the Solving the Howe-Wheeler equations videos, you have seen these two equations. Phi naught is the amplitude of the direct beam. Phi g is the amplitude of the diffracted beam. Z is how much the beam has traveled into the material. What you have here is d phi over dz in a perfect crystal. With the presence of a stacking fault in the crystal, you slightly rewrite these two equations into this. The additional term is exponential 2 pi I g dot r, while everything else are kept the same. And 2 pi g dot r is called phase factor. This is the phase difference caused by the presence of the stacking fault. Therefore, if the phase factor 2 pi g dot r is equal to 0, there is no phase difference caused by the stacking fault, and the stacking fault will be invisible. Also, if g dot r is an integer, exponential 2 pi I g dot r will be equal to 0. The stacking fault will be invisible as well. Here, we're looking at the differential form. We can also just look at the amplitude of the direct beam and the diffracted beam. The top part shows you the amplitude of those two beams when the crystal is perfect. The bottom part is when you have a translation defect. Again, the paths highlighted by the red lines remain the same. If g dot r is equal to 0 or an integer, the top and the bottom paths will have the same expression. The stacking fault will be invisible. Let's look at the example on the right. The stacking fault is inclined and we have electron beam coming from the top. And assume the stacking fault is visible. The extra terms in the bottom two equations will contribute to the contrast. The amplitude of the beam will oscillate similar to that from the thickness fringes, which will give you the stacking fault fringes in TEM images. If the stacking fault is visible, and if you do very careful two-beam bright field and dark field images, you can actually learn a lot about the stacking faults you are imaging. Here, we'll describe the fringes to be white and gray instead of white and dark. There are a number of rules. First, in bright field TEM images, both the top and the bottom of the stacking fault have the same contrast. A and B in this example are bright field TEM images. In A, you can see both top and bottom are gray. In B, both top and bottom are bright. In dark field, for stacking faults, the top and the bottom they have complementary contrast. C and D are dark field images. In C, you can see top is gray, bottom is bright. In D, top is bright and the bottom is gray. The top and the bottom are used just now refer to the position of the stacking fault in the micrograph. It has nothing to do with where the stacking fault intersects through the specimen. Also, based on the 4 micrographs on the left-hand side of the slide, we can work out how the stacking fault cuts through the specimen. For example, on which side the stacking fault cuts through the top surface of the specimen. on which side the stacking fault cuts through the bottom side of the specimen. We can also tell whether the stacking fault is intrinsic or extrinsic. I will not expand it here. If you are interested in this part of stacking fault imaging, you can pause the video and read the notes I prepared for you on the right-hand side of the slide. In dislocation imaging, which we'll discuss in the next video, you can do multiple G.B conditions to determine the Burgers vector of the dislocation. In a very similar way, you can do different G.R conditions to make stacking faults visible and invisible to determine the fault vector. This is a really good example from Eddington's book. By selecting different G vectors, you can make some of the stacking faults appear and disappear. I just realized there is one fundamental concept I forgot to mention. Stacking fault is caused by the dissociation of a dislocation. So you have a stacking fault bounded by two partial dislocations. In the example shown here, if we look at stacking fault A, these are the two partial dislocations. In addition to stacking faults, we also have other translation boundaries. One example is the antiphase boundary. Antiphase boundaries are widely observed in intermetallics. The main difference between antiphase boundary and a stacking fault is, in addition to the stacking difference, there's also a chemistry difference. Since both stacking faults and the antiphase boundaries are translation faults, we can pretty much apply what we have learned from stacking faults imaging to antiphase boundary imaging in TEM. In the next video, we'll move to a more ubiquitous defect, dislocations, and discuss how we can do dislocation imaging in TEM.